So thanks to Greg and Gennady for organizing this symposium and for inviting me to present some of the work that's being done as part of IRG2 on ultrafast control of the functional properties of complex oxides. So complex oxides are a huge family of materials. The particular subfamily that I spend most of my time working on are the perovskites. Many of the functional properties of perovskites are connected to one or more vibrational or phonon modes of the material. So probably one of the most well-known examples of this link is that of ferroelectricity. So if we take the classical ferroelectric lead titanate, the small atomic displacements away from the high symmetry cubic phase or that characterize the ferroelectric tetragonal phase can be thought of as a frozen inversion of one of the zone center phonons of this high symmetry cubic phase. And there are many other examples of the electronic and magnetic properties of perovskites being associated with particular structural distortions, but they're typically associated with zone boundary phonons. And probably the most well-known or well-studied examples of these zone boundary structural distortions in perovskites involve these so-called rotations or tilts of the transition metal octahedra. So as an example of how these kinds of modes couple to properties, in the rare earth nickelates, they go from being, they have this crystal structure, they go from being paramagnetic metals to antiferromagnetic insulators to paramagnetic insulators as a function of the radius of the A site cation. So as that cation radius gets smaller and smaller, that octahedral rotation distortion gets bigger and bigger, and this nickel-oxygen-nickel bond angle gets more and more bent away from 180 degrees, which is the value that it has in the cubic structure. And you can see similar trends and phenomena in other families of perovskites, like the rare earth manganites, and I'll say more about that family in a little bit. The thing that I want to emphasize here is that understanding the structural basis of these properties, understanding how these properties arise from the crystal structure and how they're connected with various phonon modes, has not only advanced the fundamental physics and chemistry of this family of materials, but it's really allowed the community to make tremendous progress in manipulating these properties using, for example, epitaxial strain or chemical substitution. And there are now a number of examples showing how those, what I call static techniques, can be used to tailor or manipulate the electronic and magnetic properties of perovskites. What I'm going to show you today is how we can use light to control the properties of perovskites, specifically how we can use light to change the magnetic order or effectively switch off bulk magnetism in a perovskite titanate, gadolinium titanate, which is a ferromagnet in its ground state. So unlike the static techniques that I just mentioned, here we're talking about a short-lived response, dynamical response in a non-equilibrium phase. Okay, so here's an example of such an experiment on a different family, of a material from a different family, from the rare earth manganite family. So this is praseodymium calcium manganite. And this phase diagram is very complicated. It's a function of temperature, and this X is the concentration of calcium that sits on the A site. So, as I said, it's pretty complicated, but there are really only two things that I want you to get from this. One is that the material is insulating over this whole part of the phase diagram. That's what all of these eyes are on the different phase labels. And the second thing is that when X equals 0.3, so when the A sites are occupied by 30% calcium, then the material is sensitive to external perturbations because there are lots of different phases hanging around with different properties. So what was done in this experiment was that a laser was tuned to the frequency of one of the infrared active phonon modes in this material, and it involves displacements of the manganese ions against these or opposite these oxygen atoms. And after exciting this phonon, these authors see a change in the resistivity of the material. And so they're detecting, in the reflectivity and the resistivity, but they're detecting whether the material is an insulator or a metal optically. And this change in reflectivity is consistent with an insulator to metal transition. And that transition, that metastable state, lives for quite some time after the initial laser pulse goes by. And by tuning the wavelength of the laser, they see the maximum change in conductivity occurs at the energy of that 71 millieV phonon mode that they excited. And so that's nice because it suggests that the lattice is playing a dominant role in this transition, since electronic excitations are gapped at these frequencies. Okay, so the atomic displacements that accompany this phonon mode change the crystal structure in such a way that the material is no longer insulating. So this is a cartoon of the basic physical process or mechanism or nonlinear phononics mechanism that was proposed to explain the experiments, to explain the results of the experiment that I just talked about. So you have a laser that is the frequency of which is tuned to one of the infrared active phonon modes in your material. That phonon mode gets zapped and it starts ringing or vibrating because we've just dumped a whole lot of energy into it. And in some materials there is a special coupling between the IR active modes and the Raman active modes, such that when that IR mode starts ringing, it pushes on the Raman modes and they displace in a quasi-static way. And in materials where this coupling exists, this is what the coupling term looks like. So here QIR is the amplitude of the IR mode, QR is the amplitude of the Raman mode, and A is a coefficient that tells you how strongly they're coupled together. And its value is material dependent. So in a real material, that ringing doesn't go on forever. The energy that we put in the form of light has to go somewhere, so it'll get turned into heat. And we're interested in the transient response of the material before thermalization happens. So the time scale on which that happens is material dependent, but in our case it will be somewhere on the order of picoseconds. Right, so I have some equations here because I want you to get an idea of where the results or where the data that I'm going to show you actually comes from. I'm going to be showing you theory results. We use density functional theory for a lot of our calculations, but we had to develop a model of the nonlinear phononics process. That just doesn't come straight out of a DFT calculation. So not all materials can exhibit this nonlinear phononics mechanism. Only certain space groups have the correct symmetries to allow it. And we can see that by expanding the energy of the crystal in powers of the IR and Raman active mode amplitudes. These omegas are the corresponding phonon frequencies, and we get frequencies and amplitudes from density functional theory. So to lowest order, the IR and Raman active modes are coupled through this cubic term, since we just saw. The very last term describes the coupling between the electric field of the light pulse and the polarization change in the crystal. That's just how we define the polarization. It's not important. And then we have a set of equations of motion, and the solution to these equations of motion gives us a set of IR and Raman phonon amplitudes, which we add back into our crystal structure to give us a snapshot of the dynamical response of the crystal under optical excitation. And then we can explore the consequences for the properties that we're interested in using density functional theory. All right. So we decided to start exploring this nonlinear phononic stuff using the family of perovskite rare earth titanates. So they have this orthorhombic crystal structure that is sort of has these octahedral rotations or octahedral tilts that's characterized by those distortions. And the electronic and magnetic properties depend on the magnitude of those distortions. So for larger rare earth cations and smaller octahedral rotation distortions, the spins on the titanium ions align in this G-type antiferromagnetic configuration. So those red and blue spheres represent different spin up and spin down. For smaller rare earth cations and larger octahedral rotation distortions, the spins on the titanium ions align in this ferromagnetic way. This dotted line that you can see in the middle, sort of connecting these two parts of the phase diagram, means that there are no stoichiometric compounds that exist in there. But if they did, then these authors, Mochizuki and Amada, speculated that they would have this A-type antiferromagnetic order. As far as we're aware, through our searches through the literature, it hasn't been possible to experimentally realize that magnetic phase using either solid solutions or epitaxial strain, so with thin film growth. So we thought, well, maybe we can use light to realize that phase. So we decided to start with gadolinium titanate, so it sits on the ferromagnetic side of the phase diagram, and we wanted to see if we could push it over into this A-type AFM part. Okay, so these are the results from our simulation. So for excitation of a 70.5 millieV IR active phonon of gadolinium titanate polarized along this long axis. And the plot shows the difference in energy between the A-type AFM phase and the ferromagnetic phase as a function of peak electric field of the incoming light pulse. And positive energy differences indicate that the ferromagnetic phase is more stable. So you can see that all of these energy differences are positive, so the ferromagnetic phase is more stable over this whole range of peak electric field values, but it's getting quite close to the A-type AFM phase. You could say, well, you can just keep going and keep dialing up the knob on the peak electric field. For these kinds of experiments, 7 megavolts per centimeter is considered a kind of modest field. There are fields of well over 10 megavolts per centimeter that people use. But ideally, you want that to be as low as possible to minimize sample damage. So, okay, we need some way to position gadolinium titanate closer to the phase boundary. So we thought, well, let's try epitaxial strain. So this little plot again shows the energy difference between different magnetic orders as a function of both tensile and compressive epitaxial strain. So the A-type AFM phase is always closest in energy to the ferromagnetic phase. And you can see that by using strain by itself, you can push the system over the phase boundary to that A-type phase, but that's a pretty large strain. And is probably not realizable experimentally, at least not easily. But we can see how strain is moving the system closer to that phase boundary. So if we look at the exchange constants, JC is the out-of-plane exchange constant, and by convention, or by our convention, positive is ferromagnetic and negative is antiferromagnetic. So under tensile strains it goes antiferromagnetic, and just looking at the transition temperature within a mean field model. So we decided to back off on the strain a little bit and go back to 1.5%, so that's a more reasonable strain. So there the system is perched sort of right on the edge of this transition. And now if we excite the same phonon mode as before, we see a transition from peak electric fields where the ferromagnetic phase is stable to ones where the antiferromagnetic phase is stable, and at slightly more modest values than that 7 or 10 megavolts per centimeter. So this A-type AFM phase doesn't exist in the equilibrium phase diagram of any of the rare earth perovskite titanates, but it might be able to be dynamically accessed in strained gadolinium titanate. So there's a lot more to this work, but I'm standing between you guys and the coffee break. So I just want to acknowledge my postdoc guru, Khalsa. This was all his work. He did an awesome job. And all of the details are in our paper that came out a few months ago. We understand the structural basis of that change in magnetic order, and there's a lot more stuff in there too. Thank you very much for your attention, and I'd be happy to answer any questions.
Okay, questions, please. Yes.
How big are the samples you're modeling?
So we have 3D periodic boundary conditions, so there are no surfaces.
Right, and the laser field is just uniformly distributed throughout?
We don't have, the laser is not in our simulation. So in our model, we assume that the light pulse has dumped its energy and it has gone past, and all we have left is the mechanical energy. And then we take account of basically through the delta P dot E term in that energy expansion. There we set the characteristics of the laser pulse. That's done. That's like a numerical simulation. It's not like in the DFT calculation, if that makes sense.
I think there was somebody in the back. Yes, and you'll be next. Yes, please.
Okay, thanks. You demonstrated the non-linear effect on single crystal. So is it possible to see the similar effect, or the restriction? Can we get similar, non-linear effect on micro size, crystal structure instead of single crystal?
So you're asking about the role of defects, basically, or?
Or we really focus only on single crystal specific orientation, or I can have bunch of micro size crystal but oriented differently. Can we see similar non-linear effect?
So the important thing here is, let me see. I mean, off the top of my head, it would probably be possible, but there would be, the crystal has to be, the light has to be polarized along a certain direction, and so you have to hit that phonon mode along a certain direction. And so if you don't, then you're not going to see this exact effect. So in that sense, actually, it would be much better if you had an oriented thin film or a single crystal.
Greg?
So I'm expecting that the calculations were all done in a zero temperature calculation. That's the usual case for DFT. It's hard to do with temperature. But just to get a sense of the scale, thermal excitations of these phonon modes, how do they compare to the optically excited IR amplitudes? And then would thermal excitations cause any, like would it become important to know, like there's some random phase going on and then you hit it with a laser with a fixed phase, is that going to matter, or does it get dwarfed by the laser excitation?
So all of these experiments are done at very low temperatures. We have to, because here the nail temperature is 30 Kelvin. So you'd want to be below that and as low as possible. And in the experiments that I've seen, the temperature change is controlled to within about 2 Kelvin. So the experimentalists claim that they can distinguish between thermal excitations and excitations due to this mechanism. And but as part of our IRG, one of the things that we want to do is design an experiment where it's unambiguously due to the lattice and not due to thermal effects. Does that answer your question? Yeah. Okay.
Okay, I'll ask a question. So what is the frequency of your Raman mode compared with, say, inverse of the laser pulse duration? Is it much higher or much lower?
So the Raman mode frequencies, the frequencies in perovskites are between sort of 100 to 800 inverse centimeters.
Well, this is probably the IR frequency, right? Not the Raman mode frequency. I mean, is there any hierarchy of frequencies here?
Then
IR mode versus Raman mode versus your pulse duration.
Not really, and it's not just one. So I presented a model in which there was only one IR mode excited and one Raman mode that was excited. But in reality, all the Raman modes that are allowed to be excited by symmetry will be. So there are a number of Raman modes that are in play that span a range of frequencies. And the same with the IR mode. So all modes that transform like the same irreducible representation as the excited one are coupled and will be excited. And that frequency range is up to about 800 inverse centimeters.
Okay, thank you. Okay, you have a question, please?
Gadolinium was over on the left-hand side of this forbidden region. Samarium was right on the edge of the right side. Can you move down?
So that was our initial idea, was to start with samarium, but before we sort of got really deep into this project, we did a whole bunch of checks to make sure that within our sort of DFT model we could get the crystal structure right, get the lattice constants right, get the right magnetic ordering, and with samarium we were not able to get DFT was not able to predict the correct magnetic ground state. So that's why we went with gadolinium. Yep.